Okay, so today's class will be a big topic, which is important for the protein section. So we will talk about is Maillard reaction. Maillard reaction you heard about in different classes here and there a little bit, but we will talk about it relatively comprehensive, okay, in this for the chemistry class. First of all, what is Maillard reaction? This is discovered by Louis Maillard. He is a French chemist. He had a middle name, but I don't know how to pronounce because I don't know French. Louis Maillard, a French chemist, in 1912. What he found is glycine. So we know the structure of the glycine. That's the easiest amino acid with glucose. And glucose, we also know the structure. We'll draw this today again and again. So let's draw here first. We draw usually is a ring circle. So I like to draw this, so we're going to talk about it. With glucose, what did he find? He finds that at room temperature, with extended storage, and it turns brownish color. I don't have a brown. I will be using kind of this color to turns brownish color. So this is what he find originally. Okay, now later on, people say Maillard reaction is a non-enzymatic browning reaction. So we need to introduce you very briefly what is called enzymatic browning. That's something you need to know first. Let's not talk about non-enzymatic. What is enzymatic? Okay, enzymatic browning, we had this happen very often in our lifetime. But you may not recognize it. Sometimes you feel about it. Let's say I have an apple. Okay, I have an apple like this. Okay, I'm going to cut in piece. So I cut half. I cut half of the apple. And I put it at room temperature, about like half an hour. And what happens? It slowly to turn a little bit brownish color. So turns brownish color. Sometimes a light yellow, a little bit brownish. What is this? This is called enzymatic browning. Now, what's the chemical reaction behind it? It is polyphenol. That's a major component of the apple. They using an oxidase, which is called polyphenol oxidase, and generate a product called melanin. And this melanin, which is a brownish color. So this is called enzymatic browning. Now, Maillard reaction is a non-enzymatic browning. So what it is? This is reducing sugar from a food products reacted with amino acids and going through a complicated process which happened is polymerization accompanied with condensation and generate a polymer. And this polymer, we give them a name called melanoidin. Melanoidin. And this melanoidin is showing you brownish color. And that is Maillard reaction. Now, we will go back to talk about this reducing sugar. These amino acids, there can be free amino acids in a food products, or it could be amino acids from a protein or even a peptide. Okay, so that's something we need to know. An overview equation of Maillard reaction. Reducing sugar with amino acids, going through polymerization, condensation, then generate a polymer. And that polymer is melanoidin and showing you brownish color. So we're going to talk about this reducing sugar then. So what it means reducing sugar? And I give you some of the example. Glucose is reducing sugar. Maltose is reducing sugar. Lactose is reducing sugar. And fructose is reducing sugar. However, there is a very important sugar which is using in our everyday life to make the table sugar, which is called sucrose. Sucrose is not a reducing sugar. And I tell you, Dr. Martak will ask you this question during the defense. What is reducing sugar? What is not reducing sugar? So we gave you some of the example. Now let's talk about the story behind it. What's a reducing sugar for? Okay, so let's talk about, we're going to do like this to make sure we have enough space. So that's introduction go here. Okay, we talk about reducing sugar. What is reducing sugar? And you need to know reducing sugar, which means it is a reducing agent. They reduce other chemicals, and for themselves, during the reaction, they will be oxidized. Okay, this is you need to know, oxidized themselves. That's a basic chemical reaction. Okay, go back to the question, what's reducing sugar? Let's talk about glucose. So we have a structure there, we're going to draw it again. So why glucose is the reducing sugar? From chemistry standpoint, you draw the ring circle, HOH, go down, HOH, okay, OH on the top, the D-glucose, H, then we have OH, H, H, CH2, OH. Let's say I'm going to cut right here. The ring I cut it right here, what is it going to become? I skip draw most of that, okay? What it will become? CHO. What is this? This is the aldehyde group. We call it a hemiacetal. Once it's opened the ring, it becomes a free available aldehyde. That is a reducing agent. Okay, this is first example. The second example. But how about lactose? Okay, this is a monosaccharides. Lactose is a disaccharides. Okay. So first of all, what is the components of lactose? Lactose is composed by glucose and galactose. They are exactly the same looks. The only difference is this carbon number 4, that OHs go up. Okay, so we borrow this. We're gonna draw a picture here. Okay. Because it's for the chemistry class, so we're gonna talk about chemistry. Okay. Otherwise, it's all conclusions. It's kind of really boring. No chemistry at all. What happened is this guy is go up, and this is go down. Then these are the same. So this is galactose. When they combine, what happened? I skip all these, okay? I make it a little bit brief. Of course, there's O here, there's O here. What happened? There is a majority happens is right here. This is 1,4 glycosidic bonds. When they connected, if you cut it here, this hemiacetal still existing. That is important. But what about sucrose? First of all, you need to know the components of sucrose. Sucrose is composed by glucose with
fructose.
Yes, fructose. That's different. What's the difference? Glucose is a aldose. How about this guy? It's a ketones. Yeah, ketones. It's different. So how they connected? We have to draw it again. This is a very important concept here. We need to explain to you. And then we go to the conclusion, okay? This is the glucose. We'll draw several times today, so we need to know this. This is glucose. Okay, what is fructose then? We know about it. It looks like this. Okay. CH2OH. This is OH. Then you have H, OH, OH, H. Be careful here, is H. CH2OH. This is fructose. Okay, what is sucrose looks like? They connected here to here. And if you want to draw, they put an O there. So, on the top glucose, this is 1 prime. On the bottom fructose, this is 2 prime. Therefore, this is 1,2 glycosidic bonds. And we call this is a seal, okay? Acido, sorry. This is not hemiacido, which means no free available aldehyde. This is aldehyde. Now, this is from chemistry standpoint. It sounds complicated. There is an easiest way. What's the easiest way? No problem for these monosaccharides. You understand it because there's a free available hemiacido. Disaccharides. If something like lactose It is 1,4-glycosidic bonds. We call it head to tail connection. They will have hemiacetal, which means there is a free available aldehyde will be generated. But the sugar, the disaccharides like sucrose, this is we call head to head connection. There is no free available aldehyde. You could draw by yourself maltose. What is maltose? It's glucose with glucose. Same as lactose. The only thing is this H is go down. Okay, you can draw by yourself. Just give you a hint. Maltose is glucose with glucose. Same 1,4-glycosidic bonds. Okay, same thing. You can draw by yourself. You can treat this as your homework. That could be a question you ask students. Is that right? That you said you're going to generate your own question. That could be a question. Okay, so that's what we talk about is reducing sugar and what is not a reducing sugar. Always remember, sucrose is not a reducing sugar. Dr. Mataka is going to ask you, okay? I already tell you the answer. Okay, so we mentioned about this major issue. Next one, we want to talk about Maillard reaction. So we're going to draw like this. Maillard reaction is kind of complicated. Lots of the people do the research, talk about the mechanism behind it. Who did a good job? Is Dr. John Hodge. Dr. John Hodge, 1996. He is a food technologist at USDA, ARS at Illinois, a suburb of Chicago, about like 1 hour away. He's a food technologist there. He worked there 1941 to retired 1980. Around 1950s, he had one paper which is published at Journal Agriculture of Food Chemistry, which is well explained the mechanism after multiple steps of the Maillard reaction. So, Maillard reaction in some of the textbook, we also call Hodge-Maillard reaction. But this is people added later on, okay, because people want to memorize Dr. John Hodge. His whole life, the most contribution is this paper. The paper is about like 30 pages, and I can print it out for you. And our textbook, which is cited, his mechanism behind it. And that paper has a citation, is more than 1,000 at non-internet time. This is a very huge, more than 1,000 citations. It is a very huge contribution. You know, right now you have a paper cited by 500, 5,000. That's not achievements, because there's a computer, you can download it, you can do. By the time there's no internet, this paper, you have to go to library to print it out. He got about like more than 1,000 citations. It's a big achievement. So, in this class, we will talk about the mechanism behind the Maillard reaction is based on Dr. John Hodge's paper. This is also called Hodge schedule. I call it a Hodge schedule. Some people say Hodge sketch. It's the same thing. Okay, so what's the story there? There are multiple steps. At the beginning, it is usually a D-glucose. a D-glucose started to working with a free amino acids group. They will generate products called N-substituted glucosamine. And I will show you the detail on the side of the blackboard one by one. Okay, that's the first step. Then the second step, N-substituted glucosamine go in multiple reaction. Basically is protonation, deprotonation, lose water, will become 1-deoxy, 1-amino ketosamine. And the second step we call amidala rearrangement. Amidala rearrangement. Okay, once you have this 1-deoxy, 1-amino ketosamine comes out, then things become complicated. Okay. It depends, different situation. There are multiple things will happen. 1, 2, basically like this. If the food products in their microenvironments, the pH is slightly acid, around 4 to 7, they will going through 1-2 enolization. They will generate a product is HMF, hydromethylfurfural, which is an aldehyde. Okay? Next, if the pH is more than 7 or 7 to 9, which is about slightly alkaline condition, they will going through 2-3 enolization. 2-3 enolization will generate reductone or hydroxy reductone. These things happen at room temperature, at a little bit higher temperature. That's all reasonable. If at a very high temperature or extended long, more than 120 degrees Celsius, the amidala rearrangement reagent could be directly become fission products. Fission products we call volatile compounds. So what are the examples? CH3. What is this? Pyrovaldehyde. It's a volatile compounds. It's a fission products. Okay. So reductone, hydroxy reductone, we're going to fill that blank. What happened? If these products generate in the food products, it showed up alpha amino acids. What will happen? It will go through a process called Strecker degradation. And Strecker degradation will generate so-called Strecker aldehyde. And we call all these products HMF, reductone hydroxyreductone strict-aldehyde, is an intermediate products. Some of them contribute to the brownish color, some of them contribute to the aroma, some of them contribute to the flavor, but with the reaction process, they all will be reacted with imine, with diamine, lose water or with water, going through polymerization, and then we measure the condensation, generate a polymer is melanoidin. And this big guy will be contribution to the typical brownish color. So that's a story of Hodge schedule. The scientific area has been doing all these works. We were very clear at the beginning, the first step. We were also very clear, had the Amadula rearrangement, although that's a different story. We also be kind of know what happens for the step 3. But the later stage, the polymerization and the condensation, it is still a big question. Because the food microenvironment is way too complicated. There are multiple ingredients there. It is hard to explain at the final stage. Okay, so next, we will using the whole blackboard on the other side. Yeah, just move in the center. Yeah, make sure this is covered. Yeah, the whole area is flat covered. We will talk about all these stages one by one. Okay, that's the key of this class. So let's talk about that. Let's talk about the first one first, and then the second one. Okay, I had a glucose. We talk about the glucose several times. It's a ring, you know about it. And I like to draw because it's every time you draw, you know something about it. You will have a different feeling. Something will happen. They are different morphology, or we say configuration of a glucose. This is the one we call it a ring, and we know there is a chair, and also we had an open ring, which is a fission configuration. In order to happen Maillard reaction, this ring has to break. Okay, they have to break. So we'll have showing up the open ring. What the open ring looks like? CHO, CHOH, COHH, CHOH, then goes CHOH, goes CH2OH. And you should know the label of this carbon number. Carbon number 1, carbon number 2, carbon number 3, carbon number 4, carbon number 5, and carbon number 6. We will be talk about these a little bit later on. So you have to open the ring. And HOH means different configuration. So we call it a D-glucose. Okay, what's the first step? During the processing, they comes out with RNH2, which is a free amino acids. What's going to happen? They will happen at the top. And at this moment, 2 to 6 6 are exactly the same. You don't have to worry about. So what's going to happen on the top? It will become CH, OH, then ONH. And the others are the same. Okay, so we can copy it. 1, 2, yeah. Then go OH, go H, then go H, OH, CH, OH, CH2, OH. What's the first one? This is called N substitute glucosamine. And this is easy. Okay. Now, second step. What will happen? They will start to happen is lose water. Minus lose water. This is also happen in the carbon number 1. So what it looks like? CH, double bonds, ON, then go down, everything stay exactly the same. Don't do anything. H, OH, go here, OH, H, then go here, CH, OH, go here, CH, OH, CH2, OH. What is this one called? Some people say this is the imine. Some people also call this a Schiff base. Okay? It's an intermediate product, so we don't care about this too much. Then next one. What happened? They will happen again at the carbon number 1. They will be sometimes attaching a proton, and then they lose the proton. So we say it is adding proton, lose proton, protonation, deprotonation, and what happened is they actually sometimes will be doing isomerization, which means structure are the same. Chemical components are the same, but the structural difference, configuration difference. Then become what? CH2ONH become C double bonds O. It's a carbonyl group. Then you go here. OH, H, CH, OH. Then go here, CH, OH. Then go here, CH2, OH. What is this one called? Right there. This is actually called 1-deoxy, 1-amino D-fructose. Because of this. And we also give them a common name. We call 1-deoxy, 1-amino ketosiamine. So what is this one we call? Amaduri products. Amaduri arrangement products. Now, there is something we want to mention. Amaduri rearrangement, Amaduri products, is basically happening is the carbon number 1. But for the products, they also could happen at carbon number 6. There is another reaction called Hence rearrangement. We will skip the process. In your textbooks, there's a figure there. It doesn't make any sense, doesn't say anything, just put a figure there. Now, what's the difference? Amateur rearrangement will generate is a ketone CME because it happens as carbon number 1 and then the carbon number 6 is hence rearrangement will generate aldo CME. Very similar, but we just skip about that, okay? So, we talk about 1 and 2, we're going to move on to this enolization. So let's talk about these one by one. Let's talk about this on the top, what happened. Okay. Okay, when you have this 1 deoxy, 1 amino, ketone CME happens. Okay, we're gonna go through at pH 4 to 7 is 1,2 enolization. What type of the products will be generated at that moment? Okay, at that moment will generate, yes. We look at this guy, COH. If the COH generates, obviously this will be double bonds. So, CH or NH. And below all these things are the same. So you can copy OH, H, C, H, OH, C, H, OH, CH2, OH. What is this one called? This is called 2' N-amino. It is a transition product. Okay, now move on to the next one. By the way, do you know what means enolization? Enolization, chemistry standpoint is complicated. That's attacking this electron, another one. We don't talk about that. It's basically is adding a hydroxy base. It is my understanding. It's an amateur chemistry. Let you understand. It's add a hydroxy base, add OH there. Now, 2' N-amino, you will notice it. Did you see this one is different? That happened carbon number 3. This is on the left. All the others on the right. So there's something definitely special there. What we have to do? We're going to remove it. So this is gone. We call beta elimination. Now, sometimes the textbook make it complicated. They will say they do protonation first, then they lose water, then the same. It will become like this. Okay. So once this happens, what's gonna be show up something special. Once this is gone, so you have a CH. Obviously, you have a double bonds here, so COH. This is double bonds only become 1. So what happened? CH or NH. Okay, you need to keep the balance. Then all the others, those 3, carbon number 4, 5, 6 are exactly the same. So you don't have to worry about here too much. But we still draw it. Okay, CH2, OH. What is this one called? This is called 2,3' NO. This is actually also a kind of like a shift base. Some people also say it's a shift base. Okay, now, then the steps goes to here. They're gonna lose water. This gonna go. Or NH gonna go. They're gonna also will be adding water at this moment. So what's the products will be generated? Everything together. CH2, all these are the same. Okay? CH, OH, CH, OH, CH2, OH. What's the name of this one? This is called 3' deoxyhexallose. Hexallose. Okay, then it started to lose water. Where they lose water? Right here. They are losing water. Happened 3' and 4' carbon. So what will happen? The top are the same. We write here, we draw here, then we go down here is CH. Then you go here is CH. Then you go CH, OH, CH2, OH. What is this? Allulose. Now they're going to go next step. Lose water again. This time where are they going to lose water? Somehow here. Okay, now what they going to become? A top or very similar, not change. But something dramatically will be changing. So here, CH will become this guy. Then CH2OH. This is the transition step. What they will really become. This is isomerization, okay? Isomerization. They will become here, that's C, that's actually CH. Sorry, CH. This is C, that's C. This is OH, CH3. This is CHO. What is this one? HMF. The full name. Hydroxy. Right here, OH. CH3, we call it a methyl. CHO, we call it a ferroaldehyde. We only sometimes call the acronym hydromethylfurfural. This hydromethylfurfural, we're working with imine, with water, going through polymerization and condensation, generate the brownish stuff, melanoidin. This whole step from the beginning to the end, it is from here to the end, okay? From here to here. Is 1,2 enorization at the pH 4 and 7. This is the one discussed in our textbook. And our textbook only stopped here. And at the beginning of the description, they said there is 2,3 enorization. There's 1,2 enorization and 2,3 enorization. And 1,2 enorization will generate HMF, hydromethylfurfural. What is for? This is for brownish color, basically. And then they say it could happen is 2,3 enorization will generate a special flavor, then end. So then what is 2,3 enorization? Okay, we want to talk about is here. Let's go this line. This happens pH above 7. We're going through 2,3 enolization. Okay, once you say 2,3 enolization, obviously it happened is carbon number 2, carbon number 3. What is happened there? At the top, there's no change. CH2 or NH. They will become CO. This is the same thing, okay? But then they taking this one, become here, and then become COH. And all the others are stay the same at this moment. So CH, OH, CH, OH, CH2OH. There's no name for this one. Go next step. So you're going to take this one off. RNH. Okay, becomes what? CH3. Then go here is exactly the same. HOH. CH2OH. What is this one? This is called 1-methyl 2,3-diacetone. Diacetone. This is we call reductone. This reductone will later on work with alpha amino acids going through Strecker degradation. Okay? We just say S degradation. We'll show you real quick what it looks like. Okay, that's 1-methyl 2,3-diacetone. This 1-methyl 2,3-diacetone will actually going through a configuration happen something right here. This will be further become, this goes up. So CH3, double bonds right here, COH, double bond, COH, CH, OH, CH2OH. This is hydroxy reductone. TON.